Okay, so I think everybody who wants to be here is here, so we can start. So today I wanted to go a little bit towards heavy ion collisions, but not really heavy ion collisions yet. A large part of the experimental activity is and in order to understand what the initial condition of a heavy ion collision is, we need to understand what the colliding nuclei are made of. So we want to do scattering of the nucleus with some simpler probe in order to study the nucleus, in order to understand what then gives you the initial state in a collision of two nuclei. So of course the simplest should be okay. The simplest way clearest way to study what the nucleus is made of would be deep inelastic scattering. So you take an electron, you scatter it off a nucleus or a proton. That's really the cleanest way to study the structure of the nucleus or a proton. And we could talk a lot about deep inelastic scattering, but and in some sense, it turns out in the end, deep inelastic scattering is also in the CGC framework. It is simpler than proton-nucleus collisions, but at the very first somehow step, it is not necessarily clear that this is so simple. So we will start with proton-nucleus collisions, which, if you do it at very lowest order, it's kind of even simpler than deep inelastic scattering. If you want to do things more properly, it gets more complicated because you have to worry about PDFs, fragmentation functions, and hadronization, and so on. So in the end, things get more complicated in proton-nucleus collisions, but we're not going to get really to the complicated part. Okay. So we'll discuss what is known as the hybrid formalism for proton-nucleus collisions. So just good. So that's the topic of today, the hybrid formalism. I remind you that I'm following very closely the lecture note, which is posted over here. You can, and I try to update it during the week when I'm somehow trying to fix typos and errors and write a little bit more stuff. So you might periodically want to check if there's an updated version. Good. So just as a motivation, so this is the kind of, when we look at proton-nucleus collisions, these are the kind of experimental data we might be interested in. This is the nuclear modification factor RPA. So here's two experimental measurements. So RPA, I think most of you know what an RPA is. So RPA is cross-section in proton-nucleus collisions divided by cross-section in proton-proton collisions for the same process. Then if you actually have a ratio of cross-sections, then it is just normalized by A, the atomic number of the nucleus. Okay, so RPA is normalized in such a way that if it was 1, then we would really, our nucleus collision with a nucleus would be just a superposition of collisions with A nucleons, and nothing more non-trivial would be happening, and any deviations from 1 are somehow deviations caused by the fact that the nucleus is not just a nucleon scattering independently of each other. So here's data from ALICE. So since this is charged particles, NSD stands for non-single diffractive. Eta CMS less than 0.3. So this is in the ALICE tracker. ALICE sits at very mid rapidity. So this is a central rapidity region. So the nucleus and proton are going approximately, not exactly at the LHC, but approximately at equal energies per nucleon in opposite directions. And here we are measuring at the middle. There's experimental data. And there's some statistical uncertainty in the data, and then there's an additional, I think, global model uncertainty, or an additional uncertainty coming from the fact that are we actually calculating the normalization factor in this ratio correctly. So that's kind of not part of these points, but here it seems to be the claim is that it's very small. And I think it probably actually is very small in this case, because if you're actually able to measure cross-section. So there's a couple of, so this is from an Alice publication. Of course, this Alice publication has several comparisons to several different theory calculations. I'm just picking out the ones that are closest to what we will be doing here. There's a couple of things called labeled saturation models. Then there's other panels in this plot that have other models with some RCBK, RCBK-MC, and IP set. Okay, so I'm not really going to go into all the way to telling you what exactly is the difference between IP set and RCBK and RCBK-MC. These are just somehow different implementations of more or less the same ideas. Okay. Yes, so the calculation we're going to be doing today isn't actually exactly what is needed for this, because this is mid-rapidity, so something that is more recent and more kind of close to the calculation we're going to be doing today is from LHCb. So LHCb sits at very forward rapidity. Okay, and that's as we will discuss, that is even better for small x. So here's again our p-led, slightly different slices in rapidity. There's experimental data, which has quite small error bars starting. Oh, I'm sorry, I forgot to fix this. There is of course a PT axis here. I think this is I think these are PTs. This is going to PT approximately 10, and this is maybe PT going up to PT equals 5, 6, 7, 8, 10. I have to check the numbers, but we're talking about a couple of GVs here. Okay, and there's a calculation from nuclear parton distribution function. So this is a collinear factorization calculation, which has big errors reflecting the fact that these are nuclear parton distribution functions that have been extracted from nuclear scattering data available before this LHCb data. And there's just a huge uncertainty because and that uncertainty basically reflects the large uncertainty in the data from which these PDFs have been extracted. And there's nothing in the nuclear PDF framework in itself that would somehow make it so imprecise. The errors in the PDFs reflect the errors in the data that the PDFs were extracted from. So that's why this is not doesn't give a very unambiguous prediction. There's another curve which is CGC, and what we will be discussing today is how to calculate this CGC curve here. Whether it doesn't exactly, well, the trend is similar to the data, not exactly. One can then wonder about what are the details in this calculation that somehow should be do not work, but we won't go there. In this lecture, we will concentrate on the basic idea of, where does the equation come from that you're using to calculate these for the proton and for the nucleus separately, and then take the ratio. And so this calculation is done in what is known as the hybrid formalism in proton nucleus collisions. Good. So that's the kind of data we might want to understand. So what is the hybrid formalism? So let's first do some kinematics, which again I think is maybe trivial for many of you, but I think it's still useful to think about it a little bit. So here we start with a proton. Proton is going that way. So the proton here has some. Let's choose our coordinate system so that it has some p plus. It's going in the positive direction, and then you are hitting a large nucleus which has some p minus. So we're taking the nucleus going in the negative direction, proton going in the positive direction. Okay, and then we measure then we measure something. And we measure something, so this is LHCb forward rapidity, so somehow the LHC convention, or the hadron physics convention, is that positive values of this eta are, well, forward. Yeah. Positive is always forward, but which one is forward depends on. In Hera, I think Hera people use the opposite convention. What is backward for Hera people is forward for LHC people. So we're measuring some particle here, and this particle, let's say that this particle has some transverse momentum, and it has some rapidity y. So this is eta, but eta is basically y. Eta is pseudo-rapidity, y is rapidity. Rapidity is nicer for theorists, pseudo-rapidity better for experimentalists. These are mostly, so charged particles, these are mostly pions, pi plus, pi minus are the largest part of them. They're almost massless. And for massless particles, rapidity and pseudo-rapidity are the same, so we're not going to care about this difference here. Okay. Good. So this is the particle we're measuring, and where does it come from? So let's calculate. Let's go to the plus-minus coordinates. So as you remember, so now we're looking at this. Now we're looking at this particle that was produced. It has a k plus, which in my normalization is the transverse momentum and exponential of the rapidity, and it has a k minus, which is just transverse momentum and exponential of minus the rapidity. Okay, so these incoming particles are, so there's some degree of freedom. Something comes in from here, and something comes in from the nucleus, and these things together generate this particle at forward rapidity. Good. So let's to be a little bit more concrete. Let me simplify my life, and go to the center of mass system. So there's A nucleons here. I'm trying to be consistent with my variables. So we will go to the proton nucleon center of mass system. That's the typically the way you do, and people always, they don't even tell you what. Nobody ever actually quotes the number for the energy of the nucleus. You always quote the energy of the nucleus per nucleon. So we go to the center of mass system. So in the center of mass system, the proton plus momentum is the same as the nucleus plus momentum divided by A, so the proton nucleon center of mass system. Okay, so we're going to be in this system, and now we are neglecting the masses. We're neglecting the mass of the nucleon here. We're neglecting the mass of the proton here. Masses are 0. So this means that, and we're taking this proton and this nucleus to go exactly at the speed of light, which means that this proton doesn't have any minus momentum. In reality, it has a minus momentum that goes like mass squared divided by p plus, but p plus is pretty large at the LHC, so we're going to neglect that. And so the first approximation, there's no minus momentum here, there's no plus momentum here, which means that if we look at the produced particle, all of its plus momentum has to somehow come from the proton. All of its minus momentum has to come from the nucleus, right? There's no other way for this particle to get both plus and minus momentum. It has to get all its plus momentum from here, all its minus momentum from here. So let's calculate how much of the plus and minus momentum of these colliding objects we are getting. So so the k plus, which is 1 over square root 2, how do I write this? I write this as k perp exponential of y divided by p plus of the proton, and then p plus of the proton. Okay. Oh, and now I need to check this a little bit more. So now we're in the center of mass system. So the energy, so the collision energy per nucleon, S is so P. Well, S is the dot product of this and this momentum. So the energy center of mass energy per nucleon is 2 P plus P minus over A. Okay, and since P plus and P minus over A are equal, we can see that P plus and P minus A are the same as, both are the same as square root S over square root 2. Okay. So we just put that in here. P plus is square root S over square root 2, and we see that this is k perp exponential of y divided by square root S times P plus. So this I will call xp. So this is the fraction of how much of the proton momentum the produced particle is taking. And a similar argument for the other minus component. It is k perp exponential of minus y over p minus. So this is k perp exponential of minus y over square root S and p minus over A. So that's the energy per nucleon. And this is XA. Okay, so this is the fraction of the nucleus momentum that my produced particle is taking. And so now you can immediately see that, of course, if that's the point of going to forward rapidity. So somehow the way I'm thinking, I'm fixing kT, the produced particle momentum. It's of the order of a couple of GeV. So kT is the order of a couple of GeV. Square root S is in the TeV range. Okay. So the k perp over square root S is a very small number. But here, when I go to forward rapidity, I have an exponential of y, and y is like, you see, 2, 3, 4, right? Exponential of 4 it's already big enough. So this means that this xp is close to 1. There's a kinematical limit. This xp cannot be greater than 1. Yes?
It should be s squared, right?
No, because
Sure.
yeah, S is GV squared, and square root S is in GV. Yeah. So P plus is GV, P minus is GV, and S is GV squared. This is why there's a square root S here. So this is kind of the order of 1, right? And we can, if we go to far enough forward in rapidity, high enough in momentum, and in k perp. By the way, this means also that there's an upper limit. Xp cannot be greater than 1. You cannot get more momentum from the proton than the proton has. So all of these curves, when you go to more and more forward rapidity, at some point there's an upper k perp cutoff which is impossible to reach. And somehow, I'm not sure, not here at the LHCb kinematics, but when you do similar things at RIC, if you go to +4 rapidity at RIC, then the maximum cutoff, then the maximum kT is a few GeV. You cannot go, and then you are really hitting this upper limit. Then on the other hand, this XA, we have an exponential of minus y. K perp of square root S is already small, and it's multiplied by exponential of minus y. So this is very, very much less than 1. Okay, this is very small. So in principle, this is an ideal situation for us to study the small x degrees of freedom in the nucleus, right? We are small x degrees of freedom in the nucleus. Our probe here is a single quark. We know that if we go to xp equals around 1/3, or xp larger than 0.1, or xp of the order of 0.3, 0.4, 0.5, basically what we have here are valence quarks. Okay, so this means that and then on the other hand, for this nucleus, we know that at small x, it's mostly gluons. So this means that we can a little bit more identify the particles that we have in this picture. So the situation that we have is that we have a valence quark. This is a valence quark from the proton. It's the valence quark that is going here. This is a quark. And then we know that one way or the other, the things that are contributing from the nucleus side are gluons. Maybe there's one gluon. Of course, maybe this momentum is carried by 2 gluons. Maybe it's carried by 3 gluons. There are lots of gluons. So, in fact, what we want to do is to go to a saturation regime where we are not really counting how many gluons, we're not counting how many gluons it takes to give this quark this momentum, but we're just saying that, okay, this quark is going through the color field of the nucleus, and it's picking up some transverse momentum. It's picking up some minus momentum, but not a lot, because it needs to go on shell. And then, of course, okay, so here this is a quark, that's a hadron. Then presumably there's going to be some fragmentation function. So this is a quark, and here there's some fragmentation function, which is telling you how the quark then fragments into a hadron. Okay, so we're going to be calculating quark production. We will calculate what happens when a quark goes through a color field. Good. Any questions at this point?
So there, the K minus definition, does the A enter the definition of XA or not?
Here my S. Okay. Written this way, not because I defined my S. S is the so square root S is the CMS energy per nucleon. So I calculated the momentum of the nucleus, momentum per nucleon of the incoming nucleus. This is how I defined S. And if that's the way I define S, and there's no additional A here, this means that, of course, because the nucleus, in principle, the kinematical limit, if I go to the other backward direction, this XA defined like this, in principle, can go all the way up to A. In practice, it goes up to 1, but it can go above. This XA can be larger than 1. The way I have, and this is the conventional way of defining things. When somehow people say, "Oh, we have LHC," this this is why what this NN means here. This is square root SNN, so nucleon center of mass energy, not actual center, not proton nucleus center of mass energy, but proton nucleon center of mass energy in a proton nucleus collision. Okay. Good. So we want to calculate a quark scattering of a color field. So now let's try to set up this problem. In a little bit of a more mathematically sound way. And now again, I'm secretly doing light cone quantization without actually saying I'm doing light cone quantization, because that would be somehow a lecture of its own that maybe somebody else could give better. Good. So I'm calculating the scattering of a quark of a gluon field. So what is my incoming state? And I'm going to do this precisely as we did last time. I'm going to have a quantum mechanical particle scattering of a classical color field. So my incoming state is a quark state. It has some, in principle, it has some transverse momentum. It has some longitudinal momentum. It has some color. Okay. So how do I draw this? I'll draw this here. So this is my quark. It comes in with, in principle, some the quark is now going in the plus direction, and it has some color I. It goes through the classical field, and then it comes out. I want to calculate so that it comes out at Q perp, in principle a Q plus, and some other color J. Okay, this is the scattering problem I want to calculate. Quark comes in with some momentum, goes out with some momentum after scattering from the classical field. Of course, this quark is kind of a valence quark in a proton going at 2 TeV energy. So I will in the end take this quark to be collinear, just for the simplicity, but somehow one could easily do this calculation if this quark is not collinear. That actually would lead to interesting things that are not really properly done, but would be interesting to look at that better. Good. So in practice, I'm going to be looking at the situation where this P perp is 0. It's coming in with a 0 momentum, but it's not going out with a 0 momentum. It really gets a transverse momentum kick from the field. Also, the other thing that I told you is that the nucleus, it has a large P minus. The nucleus doesn't really have any P plus, right? So in fact, this color field is not going to contribute any plus momentum. So this means that I'm actually going to have Q plus being the same as P plus. So I'm going to approximate that you get no color and no plus momentum from the target. This is related to what we were discussing 2 days ago, that see that no plus momentum here in the target means that this color field does not depend on X minus. The plus momentum is the conjugate to X minus. Right? So the approximation I made yesterday, or 2 days ago, that the color field doesn't depend on X minus, here in this context means that the plus momentum of the outgoing particle is the same as the incoming particle, no plus momentum coming from the target, which if you kind of look at the kinematics is natural. There is very little plus momentum in the left moving nucleus, so there's no plus momentum there for you to take. Okay. So this is my incoming state. Now the other thing about the iconal approximation, you remember we were in coordinate space, right? We solved the Schrödinger Klein-Gordon equation in coordinate space. So that's what we want to do here too. We want to move to coordinate space states. Okay. This is something that you do in elementary quantum mechanics. You always work in coordinate space. Then you do quantum field theory, and you completely forget about coordinate space, and you just will work in momentum space altogether. So here, this is a question. This is a situation where we actually are doing quantum field theory, but also in quantum field theory, you can, in some cases, and in this case especially, go to coordinate space. So I will say that my incoming quark state is a linear superposition of coordinate space states. So I P perp dot X perp. So this is why I'm kind of keeping the P perp is going to be 0 in the end, but I'm keeping it here now just to make this structure a little bit clearer. It is a linear superposition of quark states with a transverse coordinate, but still a longitudinal momentum and color I. Now, these are called mixed space states. Mixed meaning here transverse coordinate and longitudinal momentum. Right? Oh, this is an on-shell particle, so I only need kind of the 3 components of the momentum. The P minus of this state, this is an on-shell quark, is determined by the on-shell relation. So mixed space states, and this is, you can, I mean, such a Fourier transform you can always do. I mean, you can, if you don't know what this is, you take the inverse Fourier transform, inverse Fourier transform of this equation. So the coordinate space state is a linear Fourier transform of a linear superposition of momentum space states, right? And if you know how these states are normalized, and my normalization convention is written down in the notes, if you know how these states are normalized, you can easily figure out how these states are normalized. So this is my incoming state. And the incoming state, that's the state when x plus is less than 0. So that is the quantum state of this incoming quark that is coming into the collision. Okay. So then what happens in the scattering? So here it is conventional to denote what happens in the scattering by an operator S. Okay, in this, so this is just the S matrix. Right? You have heard of the S matrix, and everybody talks about the S matrix, and then you kind of tend to forget that it's a matrix and an operator. We just take Feynman rules and calculate scattering amplitudes. So here we define a scattering operator, and this is the scattering operator that is responsible for telling us what happens in the scattering of the classical field. Okay, so so we need a scattering operator that is acting on our states, and now the question is, what is this scattering operator going to do to us? Okay, why do I have a? Okay, I will get messed up if for a general state. Okay, now this is a scattering of a classical field. You remember what happens when you scatter of a classical field in the high energy limit, in the iconal approximation, where we have a quark that has a very large plus momentum. It's going through the classical field. The classical field doesn't depend on x minus, so it does not contribute any plus momentum. So we remember that the scattering, the result of the scattering is just a Wilson line. Okay, we have a Wilson line, which, remember, we are integrating over x plus, which we argue does not depend on x minus, and of course we integrate over plus coordinate, so it doesn't depend on that either. So it only depends on transverse coordinate. This is an SU. I have to check that I get the indices right. Yes, this is an SU3 matrix, so it has two color indices, I and J. I is the color of the incoming quark. Well, let me just write that explicitly. And then what I have out is a quark in coordinate space. It has still the same Q plus, and now, but now it has a color J. So my incoming state is in one color state. The scattering of the classical field, the only thing that it does is that it takes its space states, and locally at every coordinate, the coordinate space state is color rotated by an SU3 matrix, which depends on the transverse coordinate. Okay. This is the Wilson line. The path ordered exponential in this color field. And this is the only thing that we need to know about this color field. Good. And so this is the state. This is the state after the scattering at x plus greater than 0. That's the quantum state. That's the quantum state of this quark that is coming out. That is coming out of the scattering. Okay. Good. So now again, just like when we solved the Schrödinger equation, now we have really all the physics is there. Now there's a little bit of boring algebra to dig out the cross section and get 2's and pi's and so on. Just for completeness, let us actually do this boring algebra and dig out the 2's and the pi's in the cross section, which is something I'm bad at doing, especially in lecturing, but let me try nevertheless. Okay. So good. So this is the outgoing state that is coming out, and then what we want is the cross section we want the cross section differentially in this transverse momentum, right? So we want from this outgoing state, in order to calculate the cross section, so that for going into a specific momentum mode, we want to take the whole outgoing state and project out the part of it that corresponds to the momentum that we want, right? So we want, so what we want to do is that we want to calculate, take this outgoing state and project out. Okay, so now I should have had a p plus, but doesn't matter. It's going to be the same anyway. So in order to calculate this scattering, I want to take the whole outgoing state and I want to project out a quark with a transverse momentum q perp, with a longitudinal momentum q plus, and a color j. I think I want the color j. Yes. Okay. Like this, and then I want to take the outgoing state corresponding to whatever was my incoming particle, then conventionally or somehow physical reasonableness requires that I subtract the 1, and the 1 corresponds to nothing happening, right? This is so in order to get the scattering amplitude, I want to get the outgoing wave, outgoing state, but I want to subtract the incoming wave, which corresponds to nothing happening, because I want my scattering amplitude to be 0 when nothing happens, right? And so when nothing happens, this S hat is identity, so I want to subtract 1, okay? And then I take my incoming state here, P perp, P plus, and I, like this. So this combination, my incoming state, scattering operator -1, and then projected out is going to be my scattering amplitude for this process, with P perp coming in and Q perp going out. Now, conventionally, just to get things to have the right dimensions, this is we define it in the following way, that this is 2. We split out some factors, which is again what you also do in normal quantum field theory, basically similarly, but a similar idea, but not exactly the same equations. And I have to check that I'm not doing something crazy. Yes, 2q. We split out a factor of this q plus, dimensional reasons. Then we split out a momentum conserved, because you remember in this scattering, momentum is conserved. So everything is always going to have a delta function, and then the rest. So we calculate this, we split out some factors, and then the rest is our scattering amplitude for P perp going to Q perp, and colors I going to J, like this. So this is my invariant like this. Just how in normal quantum field theory you split out a 4-dimensional delta function. If you remember how if you go from matrix elements of momentum eigenstates, you split out an overall 4-dimensional momentum conservation delta function. Here I'm just taking a 2-dimensional, just the plus momentum is conserved. Here, if I think in terms of the quantum mechanics, in terms of the quantum particles, transverse momentum is not conserved, because the way the formalism is set up is that I have particle scattering of classical fields. So in a normal quantum field theory, perturbation theory, 4 momentum is conserved. The 4 momentum of the quantum particles is conserved because it's only quantum particles interacting with quantum particles. There's nowhere you can get momentum or lose momentum. Here it's a quantum particle scattering of a classical field. So the classical field contributes transverse momentum and minus momentum. So from the point of view of the quantum particles, only plus momentum is conserved because the classical field is giving you momentum. This kind of a formalism, I have to say, these kind of steps were first set up in a very important paper by Brodsky. So Björkén, no, not Brodsky, Björkén, Kogut, Soper in the early 70s. They were the ones who kind of went through this, and that somehow there's a somehow the statement there is the statement in the paper is that from these principles any veteran field theorist will just read off these equations, and so it's kind of a Ah, 2q plus 2 pi. 2 pi goes with the, there's a 2 pi that goes with the delta function. My pi is a little bit funny. Okay. So the invariant amplitude is what we want to calculate. So let's calculate it. Let's calculate it just to get. Well, I think I will. Yeah, we can try to. Good. So let's calculate this thing. So we put in our incoming state, which is d squared x perp. So I'm putting in this state as a Fourier transform. So d squared x perp exponential of I p perp dot x perp. Then the outgoing state in this equation is also a momentum eigenstate, and I need to express it in terms of coordinate eigenstates. So I have another Fourier transform, d squared y perp. Now it's a bra state, which is a complex conjugate, Hermitian conjugate. So there's a minus iq dot q perp dot x perp. And then y perp, yes, thank you. Y perp. And then I have a, so here I have a quark with y perp, color J. I'm leaving shortening the notations a little bit, s hat minus 1, and a quark with x perp and color I. Right? And then I know what my S perp, I know what my S operator does to coordinate space states. So these I can calculate, and this is just, my states are normalized in such a way that this is 2p plus 2 pi delta of p plus minus q plus. Remember that maybe I should, here there was a q plus, here there was a p plus, and there's a momentum conservation delta function, and then bji at x perp, and then of course my coordinate space state, you know that the momentum space, we know that these are orthogonal in transverse momentum. I mean, the inner product of two states with p perp and q perp is a delta function. And the Fourier transform, after the Fourier transform, also the coordinate space states are orthonormal. So the inner product of, when I multiply, when I project out the y perp state from this, I multiply this equation from the left with the y perp. This is just a number, and then I get an inner product between y perp and x perp states. And the inner product between a y perp and x perp state is just a two-dimensional delta function x perp minus y perp. And I think, yes. Now it has, in the coordinate space, there's no 2 pi squared. In momentum space, there's a 2 pi squared. In coordinate space, no 2 pi squared. Yeah. Good. So this is it. So now I can use this delta function to integrate out the y-perp coordinate. Then I split out this factor. Is this factor here? So it is not part of the invariant amplitude. So what I get is an invariant amplitude for color I, p perp, going to color j, q perp, which is just d squared x perp exponential of I p perp minus q perp dot x perp b j I x perp, right? So this is now, yes, here I should have, I forgot to subtract the 1. Let me do this. So I subtracted I needed to subtract the identity operator. So times delta function x perp minus y perp. So minus delta ij in color, like this. So this now is a concrete example of, another example of one way of thinking of what does the Wilson line mean? What is the Wilson line? The Wilson line is an iconal scattering amplitude. Well, the Fourier transform of the Wilson line from coordinate space to momentum space is the scattering amplitude for a quark to scatter off the external field. I'm subtracting the 1. Good. So, so this is the one part of the physics of this Wilson line. It's the scattering amplitude for any colored particle in some representation, and then the Wilson line is a matrix in that representation to scatter off the classical field. Now again, an exercise that is similar to something that you do in some elementary particle physics course or quantum field theory course. You do it once, and then you forget it. You just use the result. So, I'm not sure when you exactly encounter this, but there's a little bit of dealing with cutoffs and infinite volumes and so on, which is kind of going from square of the amplitude to the cross section, because the amplitude is, so this matrix element is proportional to a delta function, and when you square this, you get a delta function squared, right? So a delta function squared is formally infinite, right? It's a delta function, but then this infinity is absorbed into the way that the cross section is defined as scatterings per unit time, per unit volume, and here the delta function squared gives you a delta function at 0, and this delta function 0 is the volume of the system. And then when you calculate scatterings per unit time, per unit area, then this volume cancels out. There's a little bit of derivation to go from to see how you get a cross section. This is done in normal particle physics. Here it's done in a similar way, except that there's only one delta function that you need to square. But anyway, I will not try to do this. I think the result that I write down should be relatively credible. But so the derivation goes in the same way as in normal field theory. And in the end, from this scattering, and the result of this exercise is that you get the cross section, which is I'm averaging over incoming colors, 1 over NC, right? Usual cross section thing. Then I sum over incoming and outgoing colors. And then in the cross section, there's kind of, in some sense, when you square this thing, and then half of it goes to the normalization business, and the other half remains. So I get 2p plus 2 pi delta function of p plus minus q plus, and then the invariant amplitude squared, and then phase space for the outgoing. Now this is a one-to-one scattering, right? I only have one quantum particle coming in, one quantum particle going out. So my outgoing phase space is a one particle phase space. So d squared q perp over 2 pi squared dq plus over 4 pi q plus. Remember, this is the Lorentz invariant. This is the Lorentz invariant phase space for a single particle in the transverse plus coordinates, right? So this is this is what you have. You plug this in here, and here is your cross section. So now we have calculated the cross section. I'm just plugging this in here. We have calculated we have an expression for the cross section. Now we actually have something that plugging this in here gives us something that we can actually really use to calculate these, assuming we know what the Wilson lines are. Okay. Let's simplify this. Let's simplify this square a little bit more, just to see that there is some funny aspect. There is some funny aspect in this expression. So let me calculate the scattering amplitude square. Do I also want to sum it over? Oh, yes, I want to. 1 over nc sum over I and j scattering amplitude squared. I have 1 over nc sum over I and j. I need to integrate over dx perp, dy perp. Now I'm squaring this, so I have an x perp from the amplitude and the other one from the conjugate. Oh, and let me now, for simplicity, I will take p perp going to 0 just to have writing a little bit less. This was my incoming quark. I'm taking it to be collinear. So I take the absolute value squared of this expression. I set p perp to 0. So I have an exponential of minus I q perp x perp minus y perp. Okay. And then I take the squares of these. I hope I am doing this. I hope I am doing this right. So there's the first term, which is vji at x perp, and then I write just to make this explicit. If I have something like Vij complex conjugate, I'm taking the conjugate of the amplitude. I can equally well say that so the complex conjugate is the transpose of the Hermitian conjugate. So I can write this as V dagger I j, right? Ji to ij is transposing, and transposing and taking a Hermitian conjugate is the same as taking a complex conjugate. So I have V dagger ij at y perp, and then once I get this right, the other ones are easy. It is just minus Vji x perp minus Vij dagger y perp plus delta I j, right? Good. So 2 terms with a minus sign I square, I get 4 terms. So the funny thing about this expression is that here I have I have an integral over x perp and y perp. Here, these 3 terms, none of these 3 terms depends on both of these coordinates, right? This depends only on x perp. So for this term, I can integrate over y perp easily. And I just get a delta function in q perp. For this one too, for this one also I can integrate over these coordinates. It gives me a delta function. So all of these 3 terms give me something that is proportional to a delta function in q perp, right? And I will just promptly throw these away. Yes?
Something is very weird with indices. We were multiplying the v ji with delta function. Maybe is this a trace I?
It is I'm trying to be explicit and writing a sum here over I and j. So yes, this is a trace.
No,
But here. Yeah. Yes. So these are absolutely. Absolutely, you are right. Let me correct this. Doesn't change my argument about the momentum, but you are absolutely right. So delta ij bij x perp minus delta ij. I wanted to keep the indices explicit to really make it clear, and then of course I ended up doing a stupid mistake like this. Ji y perp plus delta I. So this is delta ij squared, but delta ij squared is delta ij. Right. Good. Yes, absolutely. So you will get a trace of these. When you do the sum, it's going to be a trace. Right. So these contributions are. So these traces are somehow funny. Okay. They are somehow funny. I'm not sure how I should be thinking about them. In some sense, I think it's. In some sense, I think what happens is that there's an optical theorem. I think these terms are somehow required by the fact that there's an optical theorem, which tells you that. There's an optical theorem which tells you that the total cross-section integrated over Q perp has to be related to the forward elastic scattering amplitude. So the total cross-section somehow has to be related to the trace of this Wilson line, right? And therefore, in order for the total cross-section to have the correct value, the cross-section has to have this kind of a delta function part in Q perp. But here, we are not interested in the total cross-section. We're interested in the differential cross-section. So for the physics problem that we are interested in order to understand that kind of data, these are not interesting. So it is a little bit funny, but somehow it's, in some sense, in this cross-section, if I just identify the charge particle with a quark, or the measured hadron with a quark, kind of formally in this formalism, there's kind of some kind of a delta function peak in the cross-section at Q perp at 0 momentum, but nobody's ever going to measure that, and nobody's ever going to measure that. It's some kind of a maybe diffractive excitation or something that everything is just going forward at 0 transverse momentum down the B pipe. It's never going to be measured. We're not interested in it. Unitarity or optical theorem requires that something is there, something like that is there, but that's not where the physics is for understanding this data. So these pieces are there, but we're just gonna say that we're not interested in these pieces, okay? And we're gonna throw them away. So what remains is So what remains is just 1 over nc d squared x perp d squared y perp, and let me actually write this. Let me, to make this the dimensions a little bit clearer, I can define an impact parameter b perp, which is x perp plus y perp over 2, and then a radius, which is x perp minus y perp, okay? And then I can write this this amplitude squared as integral over impact parameter, integral over dipole radius. Sorry, my R is also not very legible. So the only thing that appears here is the difference, so exponential of minus iq dot r perp. And then now that I have thrown away these terms, the sum over I and j is just a 1 over nc trace b of x perp, v dagger of y perp, like this. So now, typically, if of course, I don't really have a very clear picture yet of what this thing is, how it depends on x perp and y perp separately. But typically, it is natural to assume that this thing is only a function of x minus y. It's kind of, if I have a big nucleus and I approximate it with a translationally invariant system, in a translationally invariant system, and then I have to take some kind of expectation value over some kind of averages in the target nucleus, it is natural to assume that this is going to be just depend on the difference between the two. If that is the case, then this integral factorizes out, and this is just the area of the nucleus, right? And then what I have is that the invariant amplitude squared is an area of the nucleus, then times a Fourier transform of this kind of a dipole, this kind of a thing, which is called the dipole operator. So this is called the dipole operator. Or dipole amplitude, or different terms. But it's a dipole because it looks like a quark and an antiquark, right? So it is actually a quark antiquark dipole. It is a quark from the amplitude together with a Hermitian conjugate of a quark from the conjugate amplitude, and a Hermitian conjugate of a quark is an antiquark. So this kind of a thing is really it looks like a quark antiquark dipole going through the target. Just a quark antiquark dipole made out of a quark in the amplitude and a quark in the conjugate amplitude, and corresponding to a single quark scattering of the target. So this is kind of this dipole operator is the basic building block in cross sections. Because it's a dipole, it's actually something that you also measure in deep inelastic scattering. In deep elastic scattering, you actually have a virtual photon which splits into a quark antiquark dipole, and there it's quark and antiquark in the amplitude already. But you have the same, if you measure the same color field in the same nucleus in a deep inelastic scattering experiment, you measure the same dipole operator. When you express the cross section in terms of the same dipole operator. Good. Now I think let's take a break, and then this is kind of the end of the calculation, but we'll take a break and we'll draw some diagrams and discuss these properties of this a little bit more afterwards. I don't know, 10 minutes, how long does it take to take a coffee? Okay, so let's continue for a little while before. So that was the main part of the calculation. So a couple of things. So first, let's look at this dipole operator. So remember that the Fourier transform of the dipole operator is the scattering amplitude. So from this dipole operator, this is allows us to discuss or give a new view on what is gluon saturation. So these V's, the Wilson lines are SU3 matrices, and the product of two Wilson lines is also an SU3 matrix, right? So that gives us some constraints on what this dipole operator can look like. I don't know if this is a weird mathematics that I'm not sure you have ever seen, but let me. So this draw the complex plane of the trace of SUN matrices. So if this is the imaginary part of 1 over NC trace of any Wilson, any SU3 matrix, and this is the real part. First, you can see there's one, so I normalized with 1 over NC. So the one place you can see is that when X is equal to Y, then you just have VV dagger. It's the same Wilson line. So VV dagger, that's a unit. V is a unitary matrix. VV dagger is a identity matrix. Trace of an identity matrix is is NC. So 1 over NC times the trace is just 1. So certainly this is the place where X perp equals to Y perp. So at X perp equals to Y perp, then this dipole operator, let me call this D, or dipole, then the dipole operator is 1, okay? In general, SU3 matrices have a threefold symmetry. So if I look at the complex plane, actually the allowed values for where the trace can be lie in an area that is called an hypocycloid. I think that's the word. So this is 1, and if I draw lines with radius 1 from the origin so these are supposed to be equally large angles, so I partition the unit circle into 3 equally large angles, so 120 degrees, 120 degrees, so this is 120 degrees. The allowed values for the trace in the complex plane lie in a form that looks something like this. Now I don't remember what this distance is, but doesn't really matter that much. Okay, so this is overall, just by group theory, the fact that these are SU3 matrices, we know that this trace lies in this area. Okay, so now I'm going to argue a little bit about symmetry, and I'm going to say that these corners here are completely weird. And I'm going to say that physically what happens is that if you take some normal reasonable distribution for what these Wilson lines are, remember we haven't really said what they are, but they have to come from some kind of an averaging over some kind of internal degrees of freedom in the target. Usually the reasonable values lie on this axis between 1, take a stronger color, lie on this line between 0 and 1. If you go away from this line to have an imaginary part in the expectation value over the target, then you have some odderon, you have some parity violating things. Going here to this negative real axis is just weird. So So typically, in any parity symmetric typical expectation, typical configurations, typical models for what these Wilson lines are, they lie in this line between the trace. This trace P of VV dagger lies on this line between 0 and 1. So we know that at x equals y, it starts at 1. And then I will just claim, without further proof, tomorrow I'll introduce the MV model in which you can actually calculate things. And one can see that in the MV model you can do a calculation, and so you can see that this is true. But I think this should be true more generally, so that if x perp minus y perp is much larger than something, I will call this something 1 over qs, the dipole operator expectation value will be 0. Okay, typically. So you go from here to here. So which means that if I plot this dipole as a function of x perp minus y perp, absolute value, as a function of x perp minus y perp, so it starts at 1. So it's a function that starts at 1, and then when you take these 2 points further and further away, somehow the color fields at some point should stop talking to each other. The color field in a nucleus, in 2 points in a nucleus separated by 5 Fermi, which is like an enormous distance, the color field should not know anything about each other, and somehow the only gauge invariant uncorrelated value that this kind of a correlator can have is 0. So what typically happens is that this dipole operator, its expectation value in the target with some degrees of freedom starts at 1 and then eventually goes to 0. Okay, and the kind of the characteristic scale. So you have a function from which, on very general grounds, you know that it goes from 1 to 0. Okay, so you can on a very general argument. So you can always define a characteristic scale that says that, okay, when I'm below this distance, I'm kind of close to 1, and when I'm above this distance, I'm close to 0, right? Of course, so you can, for example, you can choose it. Okay, you can say that, okay, when do I cross 1/2? If I have a function going from between 0 and 1, when do I cross 1/2? Okay, I draw some point, and I can say that, okay, that's a characteristic scale of my function. Okay, it's typically things happen at this distance scale, and this distance scale at which this dipole operator somehow goes from being close to 1 to being far away from 1, close to 0, is called 1 over qs, and qs is the saturation scale. So qs, in this case, you can think of it as kind of a correlation length of these Wilson lines. When x and y are closer than this correlation length, then the Wilson lines are close to each other. And when x and y are further than this correlation length, then they are uncorrelated. Yes?
So in the sketch here, do you have a plateau near 0? Or
yeah, so here typically this would go like 1 minus something x minus y squared.
I'm asking this because maybe I'm overinterpreting this, but thinking maybe this would be a sign of the string.
I don't know. I don't know about strings. I don't know. I don't have such an. Well, in some sense, in the last lecture we will come to these Glasma fields, and then we'll see kind of things that looks like strings, but nevertheless have a transverse size of 1 over qs. So in some sense, maybe this would be the width of the string. But that's yeah. But that is not very. It's not very clear. It's not very clear. Okay. So good. So if as a function of coordinate I have something which goes from 1 to 0 at a typical distance scale of 1 over qs, if I Fourier transform this, which I need to do to get the scattering amplitude here, Fourier transform the k perp. Also, the Fourier transforms at k perp equals 0, the Fourier transform is just the integral over this area. So the integral over this area is kind of like 1 over qs squared, because somehow if I have something that is 1 up to 1 over qs, and then basically 0 afterwards, the integral over the two-dimensional area is 1 over qs squared. And then if it's a smooth function, the Fourier transform will somehow go to 0 also at large k perp, somehow, with some functional dependence, which depends a lot on the details of what happens close to here. But what remains the case is that if I have a characteristic scale in coordinate space, the Fourier transform will also have some characteristic scale. So typically you will the Fourier transform will, the momentum space expression will go from being kind of of the order of 1 over qs squared to being of the order of 0, or much, much less than this, at the same scale. It's a one-scale problem, so kind of different functional forms can look a little bit different, but this kind of a characteristic scale argument tells you that if it has a typical scale in coordinate space, it will have a typical scale in momentum space. The easiest example is a Gaussian. You know that if a Fourier transform of a Gaussian is a Gaussian, and the width of the coordinate space Gaussian is the inverse of the width of the momentum space Gaussian. So Gaussian would be a typical example, but I think this generalizes to other reasonably behaving Fourier transforms. So this means that if I Fourier transform, and here this kind of calculation is telling you that the Fourier transform is what I need to do in order to somehow think about momenta. The Fourier transform also has a typical scale qs. So kind of the particles that are produced in my scattering, the quarks, the quark scattering of the color field typically gets a transverse momentum of the order of this characteristic scale qs. And so this qs is the saturation scale. Okay. And somehow it has an interpretation as a correlation length of the Wilson lines. It has or 1 over correlation length of the Wilson lines. It has an interpretation of the typical momentum that a quark gets when it goes through the color fields and gets a momentum kick. Right? It has something that I will not. I don't think we will really show in these lectures, but one can argue that the saturation scale, let's say, fitting Hera data, for example, in this kind of a formalism, one can both deduce from data and argue on theoretical grounds that the saturation scale should grow when you go to larger x. So it goes like maybe x to the minus 0.3, where here in this case x, remember this is the xa was proportional to k per square root s exponential of minus y. Okay, in the case of the scattering, in the case of deep inelastic scattering, x would be the x-Bjorkane. Okay, so this comes from data, both data and somehow theoretical arguments from BK evolution, for example, BFKL, or more properly BK, would tell you that we expect that this saturation scale would grow when you go to lower x, and therefore these effects would be more important. You would also expect that the saturation scale grows when you go from a proton to a larger nucleus, because somehow the saturation scale, somehow it measures how much stuff is there, how many gluons are there. And when you take a nucleus and then you look at one point in the transverse plane where many nucleons are compressed, and into one point in the transverse plane, you have many more overlapping nucleons. You would expect that there should be more glue, and therefore you would expect that the saturation scale would be larger in a nucleus. So then, okay, is it exactly 1/3, A to 1/3, or something a little bit different? What is the coefficient here? You should, in order to do some reasonable phenomenology, you need to do a little bit of a bit more careful calculation of what the coefficient is in here. You need to think about what is a nucleon-nucleon cross-section, or what is the size of a nucleon, what is the Wood-Saxon geometry, what is the size of a nucleon compared to the typical nucleon-nucleon separation in a nucleus. So a little bit more careful job is needed in order to get these curves. But basically, this is at its heart, this nuclear, the Q as being different for a nucleus. Oh, and A to 1/3, because A to 1/3 is it's kind of the nuclear radius. So A to 1/3 is, that's how many, if you compress the nucleus into a pancake, A to 1/3 is the number of overlapping nucleons that you have at one point in the transverse plane, right? This is why this parametric A to 1/3. And so such an estimate, but a little bit more careful, is what goes into these curves. And this is my personal opinion. Of course, I don't want to. My personal opinion, maybe the authors of the actual paper might put it in a different way. But what I would say is that the reason why this RCBK-MC curve, first of all, is unreasonably large, and also has larger errors than I think it has large errors too. Well, it has large errors because there are somehow things that are fiddled around, but it's overall above 1, basically because kind of I personally don't agree with the way they are dealing with essentially the factor in front here in this relation, and that's why. So this thing that is in some sense is not very interesting from a perturbative QCD point of view, but if you want to make plots and compare to data, you also need to be careful enough with Wood-Saxon distributions and nucleon radii and nuclear radii and this kind of more nuclear physicsy kind of things. Yeah.
This was, I assume that the line laid by CGC are taking like the very thick CGC approach.
Yes.
But if relaxing approximation, taking for example like a very thin Gaussian or something like that I don't know. But I think that Paul and I have been doing some things related to that. The approach to the data is better, or?
I don't know. I have to say I don't know. So this is kind of the leading order simplest thing, and there are so many things that you can do to go away from it. I somehow going away from this iconal limit and making the nucleus, instead of being infinitesimally thin, being a little bit thicker, makes so many of the calculations so much more complicated. That typically this is not the first thing that people try to do. There's other things. I mean, essentially, a lot of the form as a function of PT. I mean, it really. I mean, essentially depends on the form of this dipole as a function of the coordinate separation, and we haven't really said anything about that yet, right? And so that can be taken from different places. Tomorrow I'll introduce the MV Maclaurin-Vennogopalan model, which makes a specific prediction for this functional form. Then one can do BK evolution, renormalization group evolution, which modifies that form. Then if you do BK evolution at the next to leading order, using the next to leading order BK evolution equation, it again gives you a little bit of a different functional form. And that in terms of somehow the functional form of this curve, that is the most determining factor. Of course, going away from an infinitesimally thin nucleus, I'm not sure I know how that would be done. There are people who are trying to do that, but I don't have a clear opinion. So there's two things. In some sense, the factor in front here determines that do you asymptote to 1 or do you asymptote to something different. But then what exactly goes into this functional form, and then it passes on to the functional form in momentum space, determines kind of how does this curve bend, right? And those are somehow the main characteristics of this plot is what is the asymptotic level and how does the curve bend away from the asymptotic. No.
What is considered this particular mechanism of particle production, in which you have a large squat which is scattered,
Yep.
gives rise to some particle production. But because this is a right range, but which fraction of the global particle production in that single rapidity region can be accounted for by this mechanism? Because if I see simplification but not the spectrum in delay and the spectrum in PP, I can also wonder that maybe there's other processes which can equally contribute.
Well, the situation in this mid-rapidity is much more complicated, right? But in some sense, at the forward rapidity, when you go to high enough in the kinematical limit, when you measure a particle that really requires a significant fraction of the momentum of the proton, then it's hard to. Then it's a little bit harder. You know, what is the other particle production mechanism that would produce such a particle? If you require that in order to get this particle on mass shell, you need to have 1/3 of the plus momentum of the proton. It's hard to have It is hard to get that hard to imagine another particle production mechanism than taking a valence quark from the proton and letting it scatter.
So you are more confident in the lower part?
Yeah, the lower panel is cleaner. It is forward rapidity. And as I said, actually these curves are not done, the mid-rapidity curves are not done using this way. Only the forward rapidity CGC calculation is actually done in this way. The mid-rapidity is KT factorization. That's actually gluon to gluon scattering, which we might say a few words about in tomorrow. Good. Other questions about gluon saturation? Let me. So just for concreteness, maybe I'll not do the derivation, but using this I'll just write down the full formula. So the full formula requires that you have some idea of where the quark came from. So the quark comes from a quark distribution in the proton. So I will just, and it's easy when you get to this point. It's easy to get. But I will just qperp dy in rapidity. So the full formula, there's a once we have gotten to this point, we all have all the 2's and the pi's and factors in place so that we can actually get this formula. As it is, and then times this 1/nc sum over colors m squared, which is there, and then now this x is determined from x. So this is the xp, x in the proton, which is determined from the kinematics. Well, it's determined from the kinematics of the quark in the way that I erased. So there's no integration here, and this formula, I think. So this is the hybrid formula. So quark from a quark distribution, just the normal quark distribution. And then this simple scattering amplitude. Then if you want to get hadrons instead of quarks, you have to take this quark production. So this is PA to quark plus X cross section. if you want to go from quarks to hadrons, you have to, the typical thing is to convolute this with the fragmentation function. So hybrid because it is dealing with a proton-nucleus collision in a very asymmetrical way. It is treating the proton in collinear factorization, and it is treating the nucleus as a CGC. So it is a very asymmetrical setup, right? And that's why hybrid. It's kind of hybrid between collinear factorization, which is just the valence quark for the proton, and CGC, which is the scattering of that valence quark of the nucleus. That's the reason for the hybrid term. Yeah, so then of course this is if you have a quark distribution, it depends on the scale, and you need to decide, okay, what is the scale? And this is a leading order calculation. This calculation does not tell you what the scale is. Typically, you take the scale of the KT or the QT of the produced hadron or the produced quark. But this calculation in itself does not tell you what the scale should be, as is usual in any collinear factorization calculation. If you do a leading order calculation, you have some quark distribution. The calculation doesn't tell you what the scale is. You have to next to leading higher order calculation, and the higher order calculation will tell you what the scale in the leading order calculation should be. But usually you don't do the higher order calculation, you just argue that, okay, it's the produced particle that sets the scale. So in that sense, this is similar, completely similar here. Good. So this is the hybrid formula, and before we finish, I'm not gonna do a calculation at higher order. Trying to get this to stay in place, but I will draw a diagram of what happens if you say that, okay, this was the leading order result. Of course, leading order in what? So you can do higher orders in many ways. We have made many approximations. We have talked a lot about the iconal approximation. Going beyond the iconal approximation is possible, but it's very hard. In some sense, when the typical jargon in the field is when people say going to next to leading order, people don't typically mean the iconal, going beyond the iconal approximation, but going to higher orders in alpha S, but nevertheless in the iconal approximation. So what kind of things, if I say that, okay, I still have my classical field, I have an iconal approximation, I still stay high energy regime, what kind of things start to happen when I go to higher orders? So what does higher order mean? Now I have a quantum particle. I had a quantum particle quark. If I go to higher order in perturbative QCD, that quantum quark can start emitting a quantum gluon. So then I have to start thinking about contributions like this, where I have my incoming. This is my incoming quark from the valence quark from the proton, for example. It emits a gluon, and now this is a quantum gluon. This is not a classical field. It emits a quantum gluon, and then together, this system of a quark and a gluon, they go through the classical field, and both the quark and the gluon carry color charge. So they both scatter off the classical field. They live in different representations, so they pick up their own Wilson lines. The quark picks up a Wilson line V. The gluon picks up, how should I write this? Let me write this as V, an adjoint representation Wilson line, right? In the amplitude. So then I can, and one thing that you can do is that you can the adjoint, the matrix element of an adjoint Wilson line you can get from the fundamental Wilson line by trace TAV TB V dagger. So you can always express adjoint representation matrices in terms of fundamental ones. I'm not sure about this. I hope this is like right like this and not V dagger V. I don't trust me. And anyway, there's a formula that it looks more or less like this. So in some sense, an adjoint Wilson line is a little bit like two fundamental representation Wilson lines. This is actually, you can see of this, think of this in the limit, in the kind of large NC limit also. In the large NC limit, one gluon is a quark and an anti-quark. So in the language of Wilson, this identity encodes that a one gluon is a quark, and an anti-quark. Okay, at large NC, this goes straightforward way. When you do the color algebra, then there are 1 over NC corrections. So this formula is exact. This is not a large NC formula, but you can kind of see how the large NC emerges from this. There's also a gluon is a quark and an anti-quark. So now if I use this formula in the amplitude, I will have so d sigma, we just write quark nucleus going to quark gluon plus x, the cross section. In the amplitude, I will have a Wilson line from the quark. I will have a Wilson line and a conjugate Wilson line from the gluon. And then from the conjugate amplitude, I will have the daggers of these. So I will have V dagger, V dagger, V. And then some color indices that I'm not writing, and then a lot of other stuff. I mean, you have to calculate this emission. So this is something that, again, you can do in light cone perturbation theory. You can do a calculation for what is the probability or the wave function. The term here is light cone wave function. What is the light cone wave function for a quark to emit a gluon? You can emit the gluon both before the target, or you can also have a configuration where the quark first goes through the color field and then emits a gluon. So both. You have to add them in the amplitude and then square, and so the expressions get more complicated. But then you get an expression which has 6 Wilson lines with some color indices here and there. Okay, so this is a part of the NLO correction. So this is so there's this kind of in some approximation, this was derived in 2005, I think. The full NLO calculation for this kind of calculation was performed about 10 years ago by Kirillik, Xiao, and Yuan. So this is a little bit more recent stuff. So and once you manage to do these kind of calculations, so they lead to several things. First of all, you can address things like just looking at this kind of a thing. You can address things like dihadron correlations. So you can ask the question, oh, what if I measure both of these, and I look at the azimuthal angular correlation between, so dihadron azimuthal correlation. In some limit, when these are very high PT, it should be back-to-back because this vertex should conserve momentum. So I can split into a very high PT back-to-back pair. And if they are very high PT, they do get some momentum from the target color field, but only of the order of QS. So if I look at very high PT, it should be back-to-back. But then when if I go to a regime where the momenta of these guys are not really very high, the interaction with the target color field messes up the momenta. I mean, it influences the momenta. By typically you're getting momenta of the order of QS from the target. So that shows up in if you mess up the 2-vector momenta, that shows up in the azimuthal angular correlation. of two particles. So you can do a calculation of dihadron correlations using this kind of thing. Then, of course, what you can also do is that you can integrate over one of these particles and then look at, so calculate two-particle production, then integrate over the other particle. That is a part of NLO corrections to single inclusive production. So if you calculate these kind of diagrams, you calculate the wave function, you calculate the color algebra, you have some idea of what these 6 Wilson line operators are like, and then you integrate. You can get NLO corrections to single inclusive particle production, so NLO next to leading order corrections to the hybrid formula. So this is the thing that was done by Kirilik, Xiao, and Yuan in 2011. So of course, in full generality, the full next to linear correction is the next to linear correction. You get some you can get some complicated equations, and somehow you just evaluate them, and you get some curve, and that's it. There's a particularly important class of these next to leading order corrections. There's the part that is increased by large logs. So there can be, in this case, there can be two kinds of large logs. There can be logs of transverse momenta. So if you do this integrate over one of these particles, you integrate over the transverse momentum of this gluon, you can pick up a large transverse log, and that goes into, that is something that then is absorbed into the D-glap evolution of this guy. So in some sense, the proof of this hybrid formula, really actually the leading order hybrid formula, comes from calculating the next to leading order formula, at least in calculating the large log, and showing that this large log that you get from the NLO expression is the right thing, has the right thing, that right D-glap splitting function, that it can be absorbed into the D-glap evolution. So that's the real proof of that formula, the leading order formula, is doing the part of the NLO calculation. You can also have a log of K plus, so K plus going to 0. So when this gluon, when this gluon becomes very soft, that leads to another renormalization group equation. That leads to Jimwalk or Balitsky-Kovchagov evolution of the target. So it leads to a renormalization group equation for these Wilson lines, BK equation. So, and both of these, to get this curve, there's a target, to get these curves, there's a target that is evolved with BK equation. Then there's the quark distribution, which is evolved with D-glap evolution. Okay. But I think this is a good place to stop, unless there are questions. Good. So I think it's time to take a break, then move Guillermo next.